Hey guys, welcome back. This is our second part of formal probability. So if you are a B student, we are going to be doing this lecture live on Friday. So make sure you don't, you can watch it beforehand, but it would be redundant in class. So anyway, A students, these will pretty well post whenever we're doing it. But for the B students, you just have to make sure you don't accidentally work ahead. So I'll try to post some stuff to help you remember that too. All right, moving on. Formal probability. So yesterday we talked about 3 different types of probability. Now we're going to talk about formal probability. Formal probability is what we deal with games and dice and spinners and stuff like that, where we know all the possible outcomes because it's like a closed finite set of things that can happen. And we also know with randomization, like if it's rolling a dice, of course, is independent, but also if we riffle shuffle at least 7 times, we know that decks of cards no longer have any residual pattern to them. They're actually truly random as well. So we know we can't really predict what's going to happen next. Even though when you're talking about like games like poker or even better, Go Fish, it's really a game of memory because there's one deck that's not being reset after each time you draw. So you know it's already been played, so that kind of actually helps you reduce the probabilities as they go. So anyway, kind of fun stuff. We're going to be talking about formal probability here. So our different types of probability are personal probability, which is an informal version of probability. We use this type of probability all the time. I know I just said all the time, so like 80% of the days probably for me, I feel like I talk about probability, but 100% of the time for this unit, right? Personal, it's basically just gives a personal estimate of or quantifying your personal degree of certainty. So what's the probability personally do you feel like of you getting an A this semester? So if you feel it's really good, you feel it's really low, how would you quantify that if you had to? Anyway, that's personal probability. That's not what we're going to be dealing with in stats. Empirical probability is based on long-run observations from samples or from simulations like we were able to do with when we're talking about the green lights, right? So that was empirical probability. It's really cool. It's based on simulations or samples, and it's pretty stinking cool. We were able to run the simulations with our calculator, which I forgot to show that to you guys. I will make a separate video eventually, and I'll show that to you. Sorry. Theoretical probability, which is what we're going to be talking about today. So it's based on models such as dice or cards or a spinner. And among all of these, our probabilities are strictly going to be between 0 and 1. So I think that's one of the next slides. All right, so with empirical probability, we had that table, and we graphed out a line graph, kind of like a scatter plot, but it's connected with a line. And we saw that eventually it converges as it approaches infinity. And the law of large numbers tells us that if it's truly independent, and so each time you approach the light doesn't change what's going to happen the next time you approach the light, and the probabilities are consistent from day to day, then it will actually converge as it approaches infinity. Now, we don't know how long it will take for it to converge. We just know that as it goes to infinity, it will converge. So the short run behavior at any given point in time, we don't know. We could have 5 red lights in a row. We could have 10 green lights in a row. We can't predict any short run behavior, but in the long run, we can say we know where it's going to go. So if I ran a separate simulation another day, I think I just flipped these. No, this is actually a separate one. We know that one will converge as well, as long as, again, it's independent and the probabilities are consistent from day to day. The law of large numbers is what we're talking about there. So we know, again, as long as it's consistent probabilities from each trial and it's independent, that eventually, as it approaches infinity, it will converge. Now, we can't guarantee that it'll converge by the time we do 100 coin flips or 200 coin flips or 1,000 coin flips. It still might not be 50%, but we do know in the long run it will settle down to 50%. In case you're curious, we will actually be able to quantify the margin of error. So we'll be able to have a curve, and it'll actually go something along the lines of this, which is really stinking cool. And so we can measure this amount of uncertainty, which we call it like a margin of error, based on where our sample size is at. Boom, mind blown. So you know where it says like plus or minus 5%, or we think 50% of Americans agree with this, plus or minus 3%. That's your margin of error. That's what they're talking about. So we know it eventually will approach the true proportion of Americans as we increase our sample size. But with a certain sample size that we have, we're able to have a certain degree of certainty. And this actually, certain degree of certainty. Oh my gosh, I'm having way too much fun with this. Anyway, that's cool stuff that we're getting into the next unit. So first we got to get the basis of all probability stuff down. So anyway, it's going to be really cool. Just wait. All right, non-existent law of averages. So if anyone even mentions the law of averages, you know they're full of crap and they haven't actually taken stat class. More than likely, you're going to hear things like we're due for something, or there's a streak going on. Whenever you hear something like that, you know that talking about the law of averages and they're full of crap. So let's say that we had 5 tails in a row. The probability of a heads is still 50%. Regardless of what's happened in the past, it's still an independent event, and it's still 50% chance that the next one's going to be heads. It's not like we're on a streak of tails, so we're more likely to have a tails, or because we know in the long run that it's going to have to balance out to 50%, that we know we're going to eventually get some heads, so we're more likely to get ahead. No, it's still 50% chance of getting ahead. The long run behavior is as it approaches infinity. It's not going to get back to 50% within the next 5 or the next 10 or even within the next 100. We can't guarantee any of that. We can kind of go back and do a margin of error thing, but that's a different story altogether. So in the long run, we know the empirical probability will approach 50% if it's a fair coin, but in the short run, we have no idea what's going to happen. All right, probability notation and Venn diagram. So good stuff. Make sure we get a solid foundation of this. So let's say the probability that you like dogs is 91%. Okay, so in the Venn diagram, we've got dogs here. I'm supposing this one is cats. And then the outside that does not like cats or dogs is going to be all the people, the sad people who don't like animals. It's okay. I mean, I don't have any pets, but I like them. I like other people's dogs, and they have the responsibility. I don't have to. It's like children. Whatever. Anyway, not going to get into that. All right, so probability of liking dogs is 91%. The probability of not liking dogs. So this would be the complement. So if you like dogs, that's 91%. So the probability of not liking dogs is all the people that don't. So either the people that only like cats or the people who don't like either. And if you notice the area in the middle, that's going to be, of course, the overlap of the two, the intersection, which is going to be the people that like cats and dogs. So you'll also notice that we can find the complement by just taking 1 minus the probability of liking dogs. 1 minus 91.91 would be 0.09. Okay, so kind of cool. All right, so let's say a couple has 3 children. We're going to revisit this one. It's pretty important just to make sure that you can get your mind wrapped around it. A couple has 3 children. The sample set of all the possible sexes of children could be male, 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 female. Okay, basically, we have all males, 1 female. The 1 female could be the youngest, the middle child, or the oldest, like the first one born, right? Or we could have only 1 male, where the 1 male is the youngest, the middle child, or the oldest. Or we could have all female. So all these outcomes are they as equally as likely. Okay, so not the combinations of the outcomes, but the specific outcomes, the permutations themselves, which permutation just means with a specific order, not just like the possibility of having 1 male out of 3 or 2 males out of 3. That would be a combination, not a permutation. Anyway, good language there. All right, so the probability of having 3 males is 0.5 times 0.5 times 0.5, which is 1/8. The same thing for having a male, male, female in that specific order, the permutation we're talking about. So in fact, all of these have the exact same probability of occurring, which is 1/8. So the outcomes are as equally as likely. But if the order does not matter, if we ask the question of what's the probability of having a certain number of girls out of 3 children, so this would be 0 girls, right? All 3 of these grouped together would be 1 female. 2 females would be these 3 grouped together, and the 3 permutations would give us that combination, right? And then this one would be, of course, having 3 girls. So our sample space this time is 0, 1, 2, or 3. Okay, those are the number out of 3 children, the number of females that you could have. And then the probability of having none is just going to be 1 out of 8. Okay, probability of having 1 is going to be these 3 permutations together, which is actually going to be 3/8. And that's why we would say that it would be very rare for out of a combination, not out of a permutation, of out of 3 children having all girls, because there's only one permutation that allows that to happen, where there are multiple permutations of birth orders for 1 female. Okay. Same thing with out of 2, that would be 3/8. Of course, you can see that blue and blue. Hey, and the color coding nice. And then out of 3 females, there's only one combination of that, which is 1/8 as well. Cool stuff, groovy. All right, so let's model some probability. So some theoretical probability. So this is dealing with models like cards, dice, spinners, etc. We'll do a lot with cards. What's actually kind of funny is, as a stat teacher, I don't like playing cards. I don't like cards. I should be good at it, but I just don't. I don't know why. I'm weird, but I should. I have cards. I have dice for us to play with in class, and we will do some games with them, but I just don't really enjoy it. My favorite game is Go Fish, and I play it with 2-year-olds, but sometimes I lose to 2-year-olds. It's okay. Maybe that's why I don't like it, because I'm not good at it. All right, so anyway, the probability of event A occurring is the number of favorable outcomes, or the number of outcomes in A, divided by the number of possible total outcomes. So if we're dealing with cards, usually the total number of possible outcomes is 52 because we're dealing with a standard deck of 52 cards. And then the number of outcomes in A are going to be the number of cards that we're looking for, right? So for instance, what's the probability of drawing a jack, king, or a queen? So here's all of our cards kind of laid out here. Jack, king, and queen are going to be all of these here. Okay, so there are 4 suits of jack, kings, and queens. So altogether, the total number of outcomes in event A, which we were defining as a jack, king, or a queen, is going to be 12. So there's 12 out of a total 52 cards, right? Then that fraction can, of course, be reduced to 3 out of 13. And of course, we have 13 different cards here. And the reason we were able to divide it because it reduced by a common factor of 4. So there were 3 out of 13, not suits, 13 cards. I don't even know the name. It's okay. Don't worry about it. All right. So our rule number 1 for forming probability is that the probability of event A occurring has to strictly be between, can't go that far, between 0 and 1, and can't go beyond it. So whether we're certain or it's impossible, improbable, or probable, or it's a toss-up right in the middle, it's some scale, some continuous scale between 0 and 1 strictly. What a beautiful visual. All right, sample space, all set of all possible outcomes, like a red light, a yellow that we stopped for, a green light, or a yellow that we went through. All right, so the set of all these possible probabilities, like 60% of the time it's red, 30% green, and then 5% are yellows that we treat as either a red or a green. Those are probably going to be different, but you get the idea. If we add up all the probabilities of the sample space, which is all 4 of these, it should add up to 1. So the probability of the sample space is 1. That's a legitimate probability assignment rule. All right, number 3, the complement rule. So pretty simple. The probability of event A occurring is 1 minus the probability of event A not occurring, which is its complement. So if the probability of A occurring is 35%, then the probability of A not occurring, the complement, which is the area within the sample space, which is the whole rectangle that's shaded in here that we're talking about, is 1 minus 35%, which is 65%. And that would be the complement. All right, set theory with Venn diagrams. So for one thing we need to know is mutually exclusive. So mutually exclusive, another word for disjoint. So it means that they're not overlapping. So it's not possible to be both. So for instance, cards are either going to be diamonds or they're going to be hearts. You can't have a diamond heart or heart diamond. They're mutually exclusive, or in other words, they're disjoint. So sets A and B are disjoint, so we show that they're not overlapping when we draw them. Now, if they're not disjoint, we'll draw the 2 sets overlapping, saying that there is an intersection of the 2. So for instance, if we're talking about diamonds and aces, there is a diamond that is an ace, so these 2 are going to overlap. The next thing we might do is actually fill in those probabilities. So what percent of cards are diamonds? Well, that's 1 out of 4, right? And then 1 out of 4 are hearts as well. But we're not done filling in the entire Venn diagram yet, because we also have the sample space the space that's outside of those. So everything else, which would be all of the clubs or the spades, right? So that's going to be 1/2 or 2/4. We just reduce the fractions. So when it comes to over here, how many diamonds do we have? Well, I think I did it here. Yeah, so 1/4 of all of them are diamonds. Now, if you notice on this one, I drew the fraction kind of overlapping because it's saying that it's the whole set here, including the overlap, the intersection between these 2. So how many aces do we have? Well, I think I might have drawn that one. No, I didn't do that. All right, so how many aces do we have that are not diamonds? Well, there are 3 out of 52 of them. How many aces do we have that are diamonds? So the intersection here is going to be 1 out of 52. There's only 1 of those, right? And then the next question we have is how many do we have that are not aces and not diamonds? Well, you can actually add these up if you want. So this is 1/4 or 13 plus 3 more, which would be 16. So subtract that from 52. This is actually 16 out of 52, so I did that one wrong. Sorry. So it's going to be 52 minus 16. Let me pull up my... All right, so we're going to do 52 minus 16, which is 36. So this actually should be 36 out of 52 are on the outside. So 36 out of 52 cards are neither aces nor diamonds. 1/4 are diamonds. 1 out of 52 are there. We could also say that there are 12 out of 52 that are only diamonds that are not aces as well. And then 3 out of 52 that are aces. Okay, so kind of cool. Make sure we know how to do that. Addition rule. So this is not a general addition rule. We'll learn that one probably tomorrow, but this is just the addition rule. So it's for a special case. When they're disjoint, then the probability of A or B, occurring is the sum of the two individual probabilities. So if we want to know what's the probability that we draw a diamond or a heart, well, diamonds and hearts are disjoint, right? There's no overlap, so it's pretty simple. All we do is add them together. So the probability of a diamond, which is 0.25, plus the probability of a heart, which is also 0.25, is going to give us a total of 0.5. So half the cards that we would draw would be a diamond or a heart. It makes perfect sense. And of course, obviously, we would have half of them are neither a diamond or a heart, which would be one of the spades or the clubs. All right, the addition rule is the union, and this is a U. It actually stands for union. We also use it for or in normal like English language. So let's say we have 35% of high schoolers in Putnam City are freshmen, and 30% are sophomores. Well, those two are disjoint because you can't be a fresh sophomore or a freshman. I don't know. You can't be both, right? You're either a freshman or a sophomore in this case, right? And while we're at it, we could add those together, which would be 65. So what's left over would be 0.35. Yeah, so basically we're saying 35% are upperclassmen. Clearly these numbers are not right, but you get the idea. So what's the probability you're an underclassman, so a freshman or a sophomore? That would be adding them together, which would be 0.65. Kind of cool. All right, independence. So two events are independent. This is going to be a pretty big theme, of course, because we already talked about it with Unit 1, and we'll even test for it with Unit 7. So this is going to be, kind of a theme running through the whole year. So two events are independent if learning that one event occurs does not change the probability that the other event occurs. So let's look at formal definition of independence. Now we'll actually be able to quantify it, which is nice. With categorical data, we determine independence by comparing marginal to the conditional distribution. So the marginal distribution is the overall. So on the Titanic, overall death rate was 60, or survival rate, that's the happy version, is going to be 32.3%. Now, if survival is independent of class, then we would expect 32% of all of the classes to survive, right, if there wasn't a difference. But when we look at the conditional distribution based on the condition of class, like right here, see if I can actually move that, then we see that 62% of first class survived, not the overall marginal of 32. So clearly twice as many as what we would have expected if they were truly independent. So clearly there's evidence of an association between the two. And checking second class, it's higher than expected, lower than expected for the crew and the third class, which is not, we've already talked about that. But yeah, clearly, and when we graph it out as well, you can see either whether we graph the survival rates, which are in blue going down, or the fatality rates, which are going up, depending on class, they're not the same across the boards. They're not even close, right? So we have pretty strong evidence that there is an association between class and survival. All right, so the multiplication rule says that if two events are independent, meaning if one event occurs, it doesn't change the likelihood of the other. So kind of going back to that one, so if you told me that you were you had a first class ticket and you were on the Titanic, then I would tell you you would have a 62% chance of survival, right? But if you had told me you were a second class or a crew, that would change the probability of your survival, right? Because they're not actually independent. If they were independent, your survival would be 32% across the board. But it wasn't independent. There was an association. All right, so if they're independent, then knowing the probability of both of them happening. This is like a U, like a union, but it's upside down, so it's actually an intersection. So the intersection is going to be just the overlap between the two. So 40% of the people on the Titanic were crew members, and 32% overall survive. So 32% survived, 40% were crew. So if they were independent, what percent of overall would be surviving crew members? So if they're independent, we want 40% of 32% or 32% of 40%. Hopefully that's not too confusing. Well, we find that by simply multiplying them, which would be 12.8%. So if they were actually independent, we would expect 12.8%. But how many did we actually have that were crew members and survivors? 20. Oh, this would be out of the overall total, which is a completely different graph. I guess we could actually calculate that though real quick. No big deal because we have the numbers. So 212 out of 2201, which was only 9.6%. So we would have expected 12.8%, but we only had 9.6%, which is obviously less than we expected, showing there's evidence of an association between there. Okay, cool. So other things that you can do, you notice that also the 40% is overlapping these two. The 32, I put it overlapping, not right there. So if I wanted to find out what percent survived but that were not crew members, all I'd have to do is subtract these two. So 32% minus that would give me some decimal, which I guess I didn't actually do that. Anyway, same thing I could do over here. 40% minus this 12.8% would give me what were crew that were not, that didn't make it. And then if I added these two together, I could subtract it to end up getting what percent were neither crew members nor survivors. Okay, so the intersection and union of sets. So the intersection is going to be the upside down U, and that's going to be the in between the two. Did I actually do it on this one? No, I don't know where I did it. All right, then the union is saying that what is the probability you're a crew member or a survivor. So this could be a crew or survivor, or it's inclusive because it could be both. So that's going to be shading all of it. So we'd have to add them all together, but we're going to have to subtract the overlap on here because it would have been counted twice among crew and survivors. So we'll talk about that later. All right, so the intersection of these two is going to be, we said 0.18. So the probability that you're a crew member and a survivor, surviving crew member is probably, I would say in English, would be 12.8%. Probability that you are a crew member or a survivor would be the sum of those two. Oh yeah, there's all the things where I subtracted them, which what we could do is we could do 40%, which is all the crew, and then we add the 0.192%, which are the ones that survived that were not crew, and that would give us a total of 0.592. Or you could add all the disjoint probabilities, which are only the crew, surviving crew, and then only survivors. And we add all those across the board, you can get that. Another way you could do it is add the 40%, which is the crew, the 32%, which is those survived, but then you have to subtract the 0.1 or 0.128 because they would have been double counted, in other words. And by the way, if we subtract that, find the complement, that's where we get this 0.408. Good stuff. We're going to do a lot more of that, so don't worry about it. Okay, so 22 minutes in. Sorry, that was a little bit long, but let's get right into the examples here. New clothing store advertises that during its grand opening, every customer that enters the store can throw a bouncy rubber cube into a table that has squares labeled with discount amounts. Tables divided into 10 regions. I'm assuming they're all the same area. Okay. 5 regions award 10% discount, 2 award 20%, 2 award 30%, and the remaining award a 50% discount. What's the probability that a customer gets more than a 20% discount? Well, first let's fill in a table. It's divided into 10 regions. That makes it easy. So the number of regions that were 10%, they said was 5, and then 2, 2, and 1. So calculating the percentage is pretty easy. So 5 is half of 10, so that's 0.5, 0.2, 0.2, and 0.1. So that's how you fill in the table. If you want to fill in the Venn diagram, notice all of these are disjoint. They're not overlapping, or in other words, they're mutually exclusive, because you can't get both a 10 and 20% or any others, right? You either get one, this one, this one, this one, or this one. And then also what's interesting is the outside part of the sample space is 0, so no one didn't get anything because the dice didn't have any blank spots, or the board didn't have any blank areas, so you at least got something, which is kind of nice. Okay, so what's the probability the customer gets more than 20%? So that would be more than 20% would be 30 or 50%. So because these two are disjoint, we can just add them together using our addition rule, right? So the probability of getting a 30 or 50% is going to be added together, which is just 30%. Kind of nice. What's the probability customer gets at least a 20%? So at least a 20% would be 20, 30, or 50. So there's 2 ways we could do this. We could add those together, which would give us 50%, or we can find the complement. The only way that we don't get at least a 20% discount is if we only got a 10%, which is 50%. Hopefully you follow that logic. What's the probability that the first 2 customers both get a 50%? Well, these are going to be 2 independent events, and we want to know the intersection of those 2. So we just simply multiply them together. So the probability the first one gets it would be 10%. The probability the second one gets it still 10%, because the dice resets. It doesn't know what happened to the person before it. So 0.1 times 0.1 is going to be 0.01, which is 1%. 10% of 10% is 1%. What's the probability that none of the first 3 customers get more than a 30%? So more than a 30% is really talking about 50% discount. So that's going to be pretty rare, right? So the fact that none of the first 3 get a 30% discount is going to be pretty common. So that would be 0.9, which is the complement of 0.1, right? So they're getting either 10, 20, or 30. So 0.9 for the first person. Again, independent event, we're looking at the overlap of these 3 events. So we're just going to multiply them all together. So 0.9 times 0.9 times 0.9 is going to be 0.729. Which probably the first customer to get a 30% discount is a sixth customer. We'll think of these as independent events. One of the easiest ways to do this is to model it out like this. So here's our first event. Probability that if the first one to get a 30% discount is a sixth customer, what does that mean about the first 5 customers? Well, it means all the first 5 customers, ... for the first 5 could not get the 30%, which the 30% means they got something else, which would be 0.8 for the first person. The second person was 0.8 as well, then 0.8, then 0.8 again, and then the fifth person was also 0.8. And then the special part is that the sixth person has to be the one who does get it, which is a 0.2 probability. So basically we're doing 0.8 5 times and then multiplied by 0.2. So 0.8 to the 5th power times 0.2 is just an easier way to write that, which would be really rare because that's a very specific thing happening, right? Yeah. Okay. What's the probability that there's at least one customer to win a 50% discount? So this could mean that among the first 5. So this could mean that 1 out of 5 get the discount, 2 out of 5, 3 out of 5, 4 out of 5, and any combinations of the orders of that happening as well. So calculating this by hand, doing it directly, would be a pain in the butt. We'd have like a tree diagram of all the different combinations of things, and we'd have to multiply them all, then add them all together. You don't want to do it that way. So the easiest way to do it, anytime you see at least one, is to find the probability that it doesn't happen, which is that no one gets a 50% discount, and then subtract that from 1. And that'll give you all the other possibilities of somebody, at least one person, getting a 50% discount. So what is the complement? So 50% discount is a 10%. So let's find the probability that no one out of the first 5 gets it. So that would be that they got something else, which is 0.9, which would be really common. So 0.9 to the 5th power would be the probability that no one gets it. Then we're going to subtract it from 1, which will give us the probability that at least one. So 1, 2, 3, 4, or all 5 get it. Anyway, put that in the calculator, you get something that's actually fairly common. So the probability that at least one person gets a 50% discount within the first 5 that play is actually about 41%, even though it's a 10% chance of that occurring. So kind of cool. And of course, the most likely outcome of that would be that just one person gets it. All right, the polling mentioned in the chapter, opinion polling. Organization contact their respondents by sampling random telephone numbers. Although the interviewers now can reach about 62% of the U.S. households, the percentage of those contacted who agree to cooperate with the survey has fallen from 43% in 1997. That's because there weren't many people calling back then. And now it's down to 14%. It's not that surprising. It's probably even less now, because that was in 2012. Pew Research Center for the People in the Press. Okay. Each household, of course, is independent of the others. Created a tree diagram for the events in 2012. So 2012 kind of labeled it. Of all U.S. households, what percent were we able to successfully contact? Well, they said they were able to reach 62%, which means that 38%, because it's the complements, either one or the other, we couldn't get a hold of them. It's kind of like when I call parents, I only have one phone number, and sometimes it's dead. So I know what they feel. It's kind of frustrating. All right, so of those who were able to contact, the 62%, what percent cooperate? So they say now it's only 14%. So 14% cooperate, which means that 86% do not cooperate. So the tree diagram kind of shows us the changes of events. This is event A, and over here we have event B, which is conditional probability based on the previous event, because it's a part of this tree branch. Okay, moving on. What's the probability that the next household on the list will be contacted but will refuse to cooperate? So they were contacted is the first event, 62%. Then of those, they didn't cooperate, which is an 86%. So all we have to do to find the probability of this branch and getting to that tree is just multiply them. So 0.62 times 0.86, which will be that. All right, what's the probability in 2012 of failing to contact a household or contacting a household but not getting them to agree to the interview? Well, we're either talking about not contacted, which is 38%, or the one that we just calculated. So we could add those two together, which would give us that. The other way to do this is by using the complement. So the only thing we're talking about that wouldn't be occurring would be is if we contacted them and they cooperated. So we can multiply contacted and cooperated, which would be this branch, and then subtract it from 1, which will tell us the sum of all the other branches in our diagram. So doing that, if you put it in the calculator, you'll get the exact same thing by doing a complement, which is pretty fascinating. All right, that's it. Right under 30 minutes. So that's I will post the next video tomorrow, and you're only going to have 3 assignments this week. If you're a B student, we're going to be doing these 2, so yesterday's and today's in person, and then the one that I'm going to post tomorrow. That one you'll have Monday and Tuesday to do it on your own. So let me know if you get stuck on anything. I'd love to help, and I'll see you guys later. By the way, it was great seeing you guys in class. I'm looking forward to seeing the B kids in class too. So it's a lot of work for me, but honestly, you guys motivate me to like do stuff and get things done. So I'm feeling great. All right, see you guys. Bye.